Hello, my name is Lewis Crabtree, and in this video I'll be discussing my solution to the pathfinding problem using the A-star algorithm for cities in the Lower Mainland. To get started, I'll show a demo of the program and then we can look at the code afterwards. So when we start the program, we get an output of the cities in the Lower Mainland along with a two-letter abbreviation for them. We can start with our start node, so for this example we'll use Vancouver, and our destination node will use Langley. We can now choose which algorithm we want to use. We can use A-star or Dijkstra's. In this demo I'll use A-star. We then get an output of the optimal path from our start node to our destination node, which in this case is Vancouver, Burnaby, Surrey, and then to Langley. We can now look at the code behind this program. This is our main method here. We just have our city names, and then we get user input for our start input, destination input, and the algorithm that we want to use. We build a graph here based on this adjacency list, which has our nodes along with the distance to each of the adjacent nodes to them. We have methods for getting our neighbors and generating our heuristic. To generate our heuristic, we look at the node we're interested in and then get its distance to the goal node, and then subtract a random number between 5 and 10 and round that down. We store this heuristic in this heuristic dictionary so that when we are interested in the heuristic for a specific node, we can just look that up here. Now that we have our graph, we can call this Pathfinder method, where we pass in the graph that we're using, the algorithm that we're using, our start node, and our destination node. In this method, with our algorithm, which has a find path method here, A-star and Dijkstra's will implement this pathfinding algorithm class. So we'll call find path on that. We can look at it for A-star first. We have a priority queue here. In this priority queue, when we put new things in it, we put in the city, the total distance so far to this city from our start node, as well as the priority. For A-star, the priority will be the distance plus our heuristic. And when we want to get something, we just get the one from the first in the list, because each time when we put it in, we will then sort it by the priority. So to start with, we'll put our start node in with a distance of 0 and a priority of 0. We have this already expanded list where we'll keep track of the nodes that we've visited already. We then have a best parent dictionary, and what we do here is for each node that we have, we'll keep track of what the shortest path to get to that node is. So while our queue is not empty, we'll get our current node to look at. This is what we're expanding, and we'll add it to our already expanded dictionary. If we found the goal, then we'll break and we'll start building our path. Otherwise, we will look at all of the neighbors for our current node. We'll get the total distance, so that's the distance to our current node plus the distance from our current node to our neighbor. We'll add a priority in the case of A-star, so we add our heuristic here to our distance and use that as the priority. We'll then check if we've already looked at this node, because if we have already looked at this node, we can consider the total distance to it. If we found a new best path to get to that node, then we can keep going with it. Otherwise, we'll restart or we'll go back and look at the next neighbor. So here we've determined that we've found a new best path to any given node. So we'll add that to our priority queue. We'll add the neighbor node, the total distance to get to that node, as well as its priority. And we'll mark down the best parent for this neighbor node as our current node with this distance. Once we've done this for all of our nodes and found the goal node, or not necessarily all of the nodes, once we've found the goal node though, we'll then start building our path. So we'll start with our goal node and then go up the chain choosing the best parent for each node that we go to, and add that to this list, to the path list, and then return that path that we found. Dijkstra's is very similar, except in this case we don't use a heuristic for our priority, so we just use total distance as the priority in the queue. Thank you.